like very common topic over the history of JSSPP. Walltime prediction and its impact in job scheduling, performance, and predictability. Dalibor, I assume it's okay to record the talk?
Yeah, sure.
Okay, please, you have the stage. Virtual stage, but nonetheless yours.
So can you see my slides, please?
Yes.
Perfect. So thank you for the introduction. Yes, I will be talking about wall times. In fact, whether we can use some prediction technique to improve them, and what is the output of such improvement. This paper is a joint work between CESNET and Karlsruhe Institute of Technology. Why is it a joint paper? We actually realized in the last JSSPP, which was in Vancouver, with my colleagues from KTH, that we both operate rather large HPC infrastructures, and we both consider to automatically adjust user-provided job wall time estimates in order to achieve different things, but in fact, the basic idea was the same. We want to improve wall time estimates and see what happens. And so we said, okay, let's start to make some simulations, some tests, and see what happens. So the question was, is it worth trying? Will it bring some benefits to improve wall time estimates? And this talk will give you some insight into this problem. I would like to warn you that I will not present only nice results, but I will also present some failed attempts. So brace yourself. So a really brief introduction into wall times. Why are they important? Wall time estimates are important for the job schedulers because they rely them when doing several things. First of all, wall time estimates are used to decide whether job needs to be killed if it's running for too long. Also, these estimates are used to optimize the performance of the system, for example, in backfilling algorithm. They can also be used to predict when and where a given job is probably going to start. And if you like to do some more interesting stuff, you can also use wall times to see whether you can stage data ahead of actual computation. Here are some few examples. The first one is backfilling. So if you are building schedule, you need wall times to see how long jobs will be executing, and then you can realize that there are some gaps in the schedule. And backfilling is trying to use these gaps to perform some reasonable computation and reduce idle CPU time. It's a very popular algorithm. And second, the bottom figure shows an example of prediction. So if you are again creating this schedule using these estimates, you can then make some rough predictions when a given job will start or how long it will wait. It's basically the same thing. Also, if you have a schedule and you know how long the jobs that are already running, when they will finish, then you can take a look at the schedule and see which job is going to be executed on which node. So you can make, if these predictions are correct, then you can do this data staging before the job actually starts. It's helpful, theoretically, because if you look at this figure, at the top part of the figure, you see a normal use case where the first job is executing, then it finishes, then you need to stage some data for the second job, which, if the job is data demanding, may take some non-trivial time, and then you can start to execute the second job. So there is this non-trivial amount of time that those CPUs on that node are idle. So what we thought is a good idea in some cases, if we are able to predict where the second job will be executed, in advance, then we can stage the data alongside the first job while it's still executing, thus saving some CPU time. So that was the motivation, that were the use cases. Of course, the problem is that those Walltime estimates, as provided by the users, are very inaccurate, and a lot of work has been done here at JSFPP and also at other venues that describe these issues. And yeah, so it's not a new topic; it's an old topic, but still relevant. The reason why the estimates are typically overestimated is that users want to prevent their jobs to be killed prematurely, and also that sometimes users are lazy, so to say, or they simply don't know how long that particular job will execute, so they give some safe choice, which is a very big number. The problem is then that all the schedules that I've shown before that are constructed using these estimates are not accurate. In fact, as the system is executing jobs, these schedules tend to get shorter because jobs are terminating earlier. What happens then is that the scheduler triggers so-called schedule compression algorithm, which fixes the problem with appearing gaps, but at the same time it invalidates all predictions and can also shuffle jobs within the schedule. In the image at the bottom of the slide, you can see on the left side there is a schedule, and the red job terminates early, which ignites the compression phase. And during the compression, the allocation of the node allocation of those yellow jobs is changed to fit in the gap that appeared after the red job terminated earlier. And so at the same time, both the predicted start times and job to node allocations changed. So yeah, we have some problem when relying on these unprecise estimates. So the idea was, as I said, okay, let's improve the Walltime estimates. This talk is not about the way how we improve estimates, because we simply used some very simple Walltime predictor. It uses historic data to come up with a replacement for the user provided estimate, and it basically looks at the user's history, see how much he or she typically overestimate Walltime, and then use this overestimation ratio to adjust the Walltime estimate of the new job. That's very simple technique. And then we performed some simulations to see whether this refined Walltimes will show some improved performance. We used 4 workloads, 2 from Parallel Workloads Archive and 2 from the Karlsruhe Institute. And we always compare 2 scenarios. The one that where the user provided estimates were used, and then the one where the predictor replaced those estimates. So that was our, let's say, simulation setup. And what we observed were our optimization criteria. So first, we of course measured whether the basic predictor can actually improve those user provided estimates. Then we look at the backfilling ratio, because there was this idea that if the estimates are very bad, then backfilling might not work very well, because all jobs look the same to it. So maybe with the better estimates with predictor involved, the backfilling ratio will be better and the system will be performing more efficiently. We also were curious about wait times, whether the wait times will change and how. And then we were also interested in the accuracy of predictions. And in this case, we look at 2 criteria. First, we analyze the predicted job wait time, which is something it's a feature that is quite useful for you if you're a user. When you submit a job and the system can tell you when roughly the job will start to execute, it's quite a nice feature. The second prediction was related to the accuracy of node allocation predictions. That's the use case where the data are staged ahead of computation. Here is a quick summary. I will go into more details soon, but you can see that in some cases you see smiling faces, which means that we were happy with the results, and in one case we were not happy with the results. That will be the end of my talk, where I will explain how we did some bad decisions and didn't improve anything actually. So let's go to the first indicator, which is the accuracy of user estimates compared to the accuracy of the estimates as provided by the predictor. These two figures show the average absolute error of either Walltime estimate provided by user or the Walltime estimate provided by the predictor. The blue line shows the absolute average error per user, and the red line shows the absolute average error as provided by the predictor. So you can see that the predictor is not perfect, but is definitely providing better estimates than users do. The second factor was the number of backfill jobs. Here we quickly realized that using better estimates doesn't automatically imply that the system will significantly increase the number of backfill jobs. The problem is that while you are making estimates more accurate, at the same time, all the gaps in the schedule are also shrinking, because the schedule is built using those estimates too. So if those estimates are more correct, which typically means that they are shorter, so the gaps are getting shorter. So there is no, dramatic effect when you use more accurate estimates, but still there is some improvement, and so this result was okay for us. Concerning wait time, in the literature you can find many analyses that either show that wait time should be better with exact or precise estimates, or that with non-precise estimates it can be better too. So we have many studies that try to analyze this behavior. Most recently, I think it was in 2010 at JSSPP, when there was this great paper that deeply analyzed whether the wait times are necessarily better or worse if you use inaccurate estimates. The bottom line here is that in our case, in these 4 workloads, the wait times on average were slightly better, but I mean like few percents, but it was due to a few extremes that we were able to reduce. When you take a look at the wait time distributions that are shown here, the colors represent the amount of waiting, and the vertical axis is the percentage of jobs. So you can see that the difference between the estimated between the results obtained by using estimates from the users and the results obtained when using the predictor are, well, slightly better, but actually there's not a big difference in the distribution. So there is no guarantee that wait time must be better if you use more precise estimates. One of the reasons for this behavior is that wait time is largely affected by the ordering of jobs in the queue, or in the queue or in the schedule. If you use simple policies like shortest job first, you are guaranteed to get a good wait time. And backfilling somehow does that, because the shorter the job is, the higher is the probability that it will start to execute very soon. So when you improve estimates, you are somehow changing the order of jobs, and sometimes you get better results, but if you change the order of the jobs in a different way, you may get worse schedules by means of wait time. At the bottom of the slide, there is a very synthetic example just to illustrate how the wait time can change dramatically for the same set of jobs. These are 3 examples with the same set of jobs and just different ordering, and you can see that the wait times are varying pretty wildly. So wait time wasn't that much interesting. What was interesting were the predictions of the start time or wait time. It's basically the same. As I said, this is important for our users so that they can better understand how their workload will be executed, how long they have to wait. So in this experiment, we measured the initial expected wait time. As I said before, as the schedule is progressing in time and jobs are completing, the schedule is subject to the schedule compression. So these initial predictions are further improved as time goes. But in this experiment, we only measured the initial most incorrect predictions, and those are presented here. So again, the blue line shows the absolute errors of predicted wait times for each job, and the red line shows the same thing when using the predictor. So you can see that again, the predictor can decrease significantly the error that is reported. Is able to decrease the error in the predicted wait time that is then reported to the user. So this was really good to see that it makes sense because you are able to give more accurate predictions. And finally, I would like to mention the problem of node allocation predictions. The question here is, can we know ahead of some job starting where it will be executed? Because if we do, we can stage the data in advance and save some CPU cycles. This is a problem that my colleagues in Karlsruhe are solving, because they are developing some system that should be using this feature to actually set up some local file system on the computing nodes in order to serve for the job, and they have some real life motivation for this use case. So we said, okay, let's try that. Let's see how it works. And yeah, again, the question is, can we know ahead where the job will be executed? If you have exact runtimes, if you know the runtimes of jobs exactly, sure, it's not a problem. The schedule is perfect. There are no surprises. But with user-provided estimates, or even when using the predictor, we realize that we are not able to predict these nodes accurately. Why? Well, it turned out that to be honest, we were lazy to develop a brand new scheduling algorithm, some clever algorithm. Instead, we were trying to fix existing ones, and it didn't work. And I will show you what we did and what actually didn't work at all. So there are several of the reasons why we failed. The first reason is that we were using backfilling to build the schedule, and we quickly realized that the backfilling may actually shuffle jobs that are already present in the schedule. Because if you want to backfill some job, you may realize that there is a place for the job, but the place is only available if you reallocate some job that is already there. In the figure, you can see that job number 4 must be moved to the top, so the nodes are changed for this job, and only then this job, the green new job, can be added to the schedule. That is perfect from the point of view of utilization. Also, the start times are guaranteed. Also, all these things are okay, but the node allocations are have been changed by this move, so that's bad. Another problem is that the schedule compression does basically the same. It also shuffles jobs when it compresses the schedule. So we have these two problems: the backfilling and the schedule compression. And our idea was, okay, so let's get rid of backfilling. Let's try first come first serve. So we will not backfill at all, and see if we have some improvement. Unfortunately, there is a obviously there is a cost when you abandon backfilling, and that's poorer utilization and worse wait time. And more importantly, we still need to compress the schedule because jobs will terminate early than expected. So this didn't help a lot. And the fact that we lost some utilization by changing from backfilling to first come first serve, that actually goes against our primary motivation to reduce the idle CPU time. So we said, okay, this was not so good, and in fact, we still have to compress the schedule. So let's solve the schedule compression issue, and we decided to use so-called job to node pinning. What it does is that we basically pin every job that is about to start soon, and we pin it to the already planned nodes. So there is no node job to node shuffling for jobs that are close to their start. Again, this is some drawback, but let me show you some results that we obtained, and then I will show you why actually they are not good. So here is an example. More figures are in the paper, but imagine that you have this question that you would like to know how many jobs know at least 1 minute ahead of their start time what is their target node. So at least 1 minute ahead, you would like to know what is the destination node, and you can use this 1 minute to stage the data in. So if you use precise estimates, precise runtimes, you will see that 88% of jobs know at least 1 minute ahead where they will be executed. So this is the baseline number, the best number you can get. And now let's see what happens if you use user-based estimates. When you use user-based estimates, you drop from 88% to 12%. So it's really bad. You basically know nothing. So, okay, let's use the predictor. It will be better. No, it's not better. Well, it's better, but not much. You go from 12% to 17%, and that's not satisfying. Let's see what is the effect of node pinning, job to node pinning. Here, there is a significant improvement. You go from 12% to 58%, which is quite a nice improvement, and it start to make sense to consider this technique. Okay, but what is the cost of this technique? As I said, this node pinning and this change from backfilling to first come first serve has some cost that must be paid. So we measured the cost, and we realized that, for example, it's just an example, when we are using our new great solution that involves first come first served and node pinning, 18% of jobs wait longer than 24 hours. That's a lot. If we use standard backfilling without pinning, normal solution, only 10% of jobs wait longer than 24 hours. So obviously we achieved some improvement in the prediction accuracy, but the cost is that we really penalized all the jobs, many jobs, by means of their waiting time. So that's a clear failure, and yeah, that wasn't the output that we wanted, but that's what we learned. So to give you some conclusion, in this paper we realized that even simple predictor is able to increase the accuracy of estimates. Backfilling opportunities are reasonably good. There is no drawback when using these improved estimates. Wait time is only slightly reduced and basically doesn't change that much. Predictions concerning job wait time are much better than they were previously, so that's very important for our users. And those node predictions, as I already demonstrated, they are not possible with standard algorithms, or at least with the way that we use them. We can get either precise schedule or efficient schedule, but not both. The problem, of course, is that we were lazy and we didn't think it through. So if we want to achieve better results in this case, in case of those node predictions, we would have to use better scheduling algorithms, some that are designed to work basically. So for example, that we would have to build an algorithm that where jobs do not overlap in time. So if one job finishes earlier, there is no overlapping job after this job being planned. So no gaps will appear, and it will work more smoothly, hopefully. And the bottom line is, in fact, not all jobs really need this advanced node predictions. So maybe the way is to just to identify those jobs that need this or can use this reasonably. Those jobs treat in a different way, and the rest should be used as normally, being backfilled and used aggressively, let's say, to keep the utilization reasonable and so on. So yeah, that's the end of my talk. Thank you, and I'm ready to answer some questions.
Thanks, Dalibor.
Dalibor, hi, can I talk? Sorry.
Yeah, absolutely. Hello.
The WorkLoad that you use, are they online, yeah? In the WorkLoad parallel archive, yeah?
Mm-hmm.
And what kind of simple model, for example, you are talking about linear models and random forest models when you talk about simple models. And what kind of features about GPUs or the WorkLoads do they have a heterogeneous accelerator in those WorkLoads that you use? And what kind of information about accelerators?
So the question is whether the workloads contain some information about accelerators or something like that.
Yeah, the WorkLoad that you use, you use accelerators or GPUs, Intel 7V. They are information about.
No, the workload we use a simulator, and the simulator is executed on a single machine, and it is it uses as an input these workloads from parallel workloads archive, but these workloads are only, it's a text file describing job parameters, and those jobs don't have GPUs. In this case, they only require CPU memory. There is no GPU being involved. So the simulation is just a replay of the workload, and the parameter you are changing is the accuracy of the Walltime estimate. And so with different estimates, the scheduler is coming up with different schedules, and that's what we analyze, how these schedules are accurate and if blah 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 all these things. So sorry, that was
I got it.
I see that.
Don't worry. And the simple models, they are linear models, random forest models.
No,
when we talk about simples.
When I spoke about simple predictor, it was imagine you're a user and you're executing workload in a system. So you submit jobs, and after some time, the system knows what were the parameters of your jobs, and it can use these known information to somehow guess what your next job will be. But there is no machine learning or AI. It's basically you take the last few jobs, see how they looked, and choose the thing what I called overestimation ratio or something like that. So basically, if you keep saying that your job will run for 1 day, but it only lasts 2 hours, then the system says, okay, your overestimation ratio is 12 or something. So it divides your next estimate by 12, and that's the new estimate. That's simple, and that's actually how it's implemented. And it was, as I said, this talk
it's a lie.
Yeah, this talk wasn't not about trying to develop a predictor. It was rather, if we use some predictor, what's going to happen in the system? Will it work? Will it be useful somehow? Yeah, that may be the correct interpretation. So yeah, sure we can.
Yeah, I got it. Thank you.
Gonzalo is asking, am I right?
Yes.
Hi, nice
Hi,
to see you.
Dalibor, how are you doing?
Good.
I have a question, and it's maybe more of a general question and maybe not so specific to the prediction itself, if you allow me. In the way you evaluate the impact of the predictions, you're looking into utilization, you're looking into wait times. When you're looking into wait times, I was interested on what are your takes of analyzing how close you're bringing your cluster to some other objectives. Like in our workload, we have these groups, and these groups have different targets in terms of capacity they're supposed to be getting over units of time, of jobs that need to go through. Do you have any thoughts on how to compare that? How to compare that your predictions are affecting your, I don't know, some fairness targets that you have in the system, or some allocation targets you have in the system?
That's a good question. Because, for example, our system is actually using the estimates to choose a queue for the job. We have different queues that have different time limits. Previously, users were choosing queues. Now they are only choosing Walltime, and the system itself does the mapping. And the problem is that long queues have access to less CPUs. So the good question here is, if we predict the Walltime in a bad way, we may either help the user or not help him at all, because the job will end up in a bad queue. If you know what I mean. That's one thing that we didn't consider. Other things like fairness, we did measure fairness somehow in the past using some magic computations, but we haven't done it yet here, because we had this, multiple goals. We tried we really was trying to solve the node prediction, because we thought this must be somehow easily done, and it wasn't. So, but we didn't have time to go deeper. But yeah, it's a good point. So sorry, I don't have something in my pocket right now.
Thank you.
So,
Any other
Dalibor?
question?
Yeah. Dalibor, I have a question.
Welcome. Good to see you.
Long time no see. More of a comment maybe regarding what you said about overlap between jobs and scheduling and shortest job force and all that. So there are some ideas from scheduling from long time ago that could be relevant here. So we had work from the 1990s on Geng scheduling, where we had this idea of alternate scheduling. So you would pack the jobs together in some way, and you have different time slots, and you want the jobs in different time slots to be aligned. So if you have a hole in one time slot, then jobs from other time slots could use that. So I think the same idea could work here. So if when you allocate nodes, you don't do it in individual nodes, but you do it in blocks, and the blocks are sort of aligned in like being powers of two. So each time you can either partition them or take them together. But in any case, it raises the probability that either you have no overlap or you have 100% overlap, which is what you really want. What you really hate is when you have just like one node is overlap and then it ruins the whole thing. So you want to sort of align them by allocating in blocks and not in allocating in single nodes, and having big blocks and smaller blocks, so that they divide each other. So that's one thing that we.
Yeah, thank you. I think I remember the picture from some of your works where was this nice figure of all these jobs ordered, and there were some patterns like those bigger jobs were somehow. I think I know which review somehow relates to this comment. So I when I read the review, I was like, oh my god, that's so obvious.
So I don't remember what I was in the review. but
they were like, don't use overlapping jobs because you should put them, right behind each other. Then you
so at least I'm consistent.
Yeah. Good to see you.
Another thing is that one of the things that really helps in reducing the average response time and wait time is if you can avoid situations where short jobs get stuck behind long jobs. So that's like the fast queue in the supermarket, where if you only have a few things, then you go to the fast queue, and if you have lots of things, you go to another queue store. So also in scheduling, that would mean that if you can, at least part of the time, divide the machine into partitions, and then you have a partition which only gets the fast jobs, the partition that takes care of the longer jobs, then you're more or less guaranteed that the short jobs don't get stuck behind long jobs, because they go to a partition that only has other short jobs. And then your average drops way down.
Yeah, I agree. The problem with our system is that it may seem large, but in fact it's composed of many small clusters where we don't have really big machines. So we have, it makes sense.
But then you can assign some cluster for. Yeah. You can assign some cluster for short jobs and another cluster for medium jobs and another cluster for longer jobs, and then have the shorter jobs move through it much faster, and then the whole average goes down because they never have to really wait a long time.
Yeah, that's true. I can do that. Thank you. Yeah.
All right. I want to thank Dalibor. It's interesting to see that some of the problems we work on are still not solved and raise interest from the audience, right? Now for the last talk, Marcus, are you the one presenting today?
Tongsheng.
Tongsheng is presenting PDAWL, Profile-Based Interactive Dynamic Adaptive Workload Balance on Heterogeneous Architecture. Tongsheng, the stage is yours.
Oh, thank you. Let me see a window. Yeah. Okay. So can you see my windows?
Yes.
Oh, okay.
Yes, we can see.
Yeah. So my name is TS. I'm from the Pascal lab in the UC Irvine. And today I will talk about the PDAWL, the profile-based iterative dynamic adaptive workload balance on Heterogeneous architecture. It's a long name. So this is an outline about introduction, background, methodology, experiment, and conclusion. So first, about the introduction and motivation, because right now, as we know, is hundreds of processing units integrated into single or multi-chip, and offer more and more heterogeneous resources such as GPU and PJ are integrated together to offer the better energy and good performance. But then the problem is how to fully utilize these resources and how to explore the parallelism. So for example, in shared memory system, the cache conflict may drop the performance greatly. And for the heterogeneous medical system, especially if some applications want to use both CPUs and GPUs at the same time, and also the application need to synchronize during the runtime. So in that case, we prefer to use the workload balance way to make sure nobody are waiting for the other side, and also the communication costs are very high for the heterogeneous computing. The target for the paper, the target application is scientific computing application. So we choose two types of application. One is Soysal, stands for the data regular app, and another is sparse matrix vector multiplication, which stands for the data irregular part. So the goal is to focus on to solve the workload balance problem on heterogeneous system. Let me see next. So let me see first introduce the background. So this paper is based on the codelet model. So what is codelet? It's a sequence of machine instruction which can act as an automatically scheduled unit of computation. It has several properties. It's event-driven, and all the communication have to through the interface, such as the input and output. And the code is a codelet is non-preemptive. Once it's run, nobody can stop, and unless the machine is down, and also try to reduce the communication. So we prefer to store all the data, all the code in local. So the right side is it's a very brief graph to show a group of codelet and the TP and the threaded procedure. So the codelet, the circles stand for the codelet, the connections stand for the communication and dependency. And also we can group we can group or cluster the several codelet together to make them become a TP, become a thread procedure. We call it TP, and then we can control them. We can mapping them use the same policy. The codelet is there is a runtime system. It's run the codelet model. It's called DARTS. Basically, it's an abstract machine, and they have two types of units. One is scheduling, another computing. For the codelet, codelet normally focused on computing, and for the TP is focused on scheduling. So from the picture, we can see this model is can scaled up to chip, to node, and also even to internet. But they have the common thing about they have in the basic unit, the cluster, they have many CPU cores or many GPU cores, and also they have the computing units and synchronization units. Then talk about then I will briefly introduce the stencil code and the sparse matrix code. The stencil code is a type of iterative kernel which updates array elements according to some fixed pattern. In the paper, we show it is 2D stencil code. It means within one time step, if we want to update one pixel, we have to consider his 4 neighbors. This is the code is naive version, a sequential code, and the right side we put I put the partition way from the is still not is not is a very simple way to partition, because we want to use both CPU and GPU at the same time, and then we can partition the workload based on this this 2D stencil code based on tile and based on basic block. And this is the brief introduction about the sparse matrix multiplication. We use the code show here is a sequential code from the SHOC benchmark, and we do some. There are many ways to represent sparse matrix. We choose compressed sparse row CSR way. And also because the sequential code we want to run it in our medical system, so we do some optimization. First, we change the sequential code to the parallel code, and to guarantee it can be run on CPU and GPU at the same time. And second, because the sparse matrix multiplication, they may not very good for the GPUs, because GPU are very good for the regular data computing. So we split so we do pre-processed data. We split data into two different parts based on the number of non-zeros per row. So we split into regular part. It can be run on GPU, and also we can split in for the irregular part will be on GPU. For regular part, irregular part will be on CPU. For regular part can be run CPU and GPU both. There is a methodology. We choose a very simple methodology. So first we build the hardware model. For example, we have CPU and GPU in our platform. We build the hardware model. It can from the mathematical model or from the other part of, for example, the machine learning part we use. And then based on this model, we can initial workload both on the CPUs and GPUs. And during the runtime, we adjust the workload dynamically. That's the basic methodology. So this part is introduce the DAWL, the dynamic adaptive workload scheduling. It's an online scheduling method, and it is based on the mathematical model. So first we build up mathematical. I will introduce briefly later in later slide to see what's a mathematical model. But here is first. We suppose we already have mathematical model, the basic mathematical model, and we partition workload. We partition data into different group. One is mapped to CPUs, another mapped to GPU. And also we can partition the whole workload, or we can partition part of that. It doesn't matter. And also during the runtime, when we run the task on the machine, and we can measure the time. We can measure the workload size, and also we can measure the type of machine we are running. And then we can adjust based on this information, the runtime information, and also based on the mathematical model, we will adjust the workload. And finally, we can reach the goal is to CPU and GPU can reach the work balance method. So here is a naive. This is a naive mathematical model. I call it naive because it's only describe very basic information about the GPU, CPU, and the others. So it's because for GPU, for example, equation 1, the GPU is copy data from host device and then computation and copy data back. It didn't consider the concurrent stream way, because if we use that way, it can overlap the communication and computation. But this model is very simple, and also it didn't think about the synchronization way, because this is for the GPU, different synchronization method costs different time. And for the CPU side, it's very simple way. It's only the number of how many cores you have, how many computation you have. And here, this model is overlook the cache and also overlook the prefetcher or any hardware optimization method. For the equation 3, it's about we can use this for the hardware selection. So if R is far larger than 1, it means the GPU is much faster. So we choose the GPU. So if R is less than 1, it means the communication between host and device is very expensive. The costs are very expensive, or the computation are not very good for the GPU. So we choose CPU. But the interesting is if very close to 1, so we choose the co-running way. So our model, our online scheduling, we're based on this very basic model and decide whether we choose CPU or whether we choose pure CPU or we choose pure GPU or we choose co-running way. Let me see. So just like I said just now, it's about the that model is naive version. They overlook a lot of information. But it has another problem. So it's the first is the complexity, because right now more and more hardware are involved in one platform. So the complexity increase exponentially with the number of hardware involved, and the accuracy drop exponentially. And so it's very hard to build a mathematical model with very high accuracy. And another point is because the mathematical model is very sensitive. If you any change of the hardware configuration, for example, if you update your GPU from K420, NVIDIA K20 to K40 or the other type or harder or upper model, you have to rebuild the mathematical model. So it's very time-consuming work. And also another thing is static. So it cannot capture the runtime situation. Based on this problem, and we propose we prefer to introduce machine learning here. We call it profile-based machine learning assist hardware model. Here I briefly introduce the several steps for to build the machine learning model. So it's here. So we need hardware information, and also we need the application profiler information. It's from the for CPU profiler or from the GPU profiler to collect during the runtime. We collect the different hardware counter for different events. And after we collect data, and we do pre-process data, we normalize data, and then because we get so many features from the profiler, so we prefer to use the traditional cluster algorithm called HAC to reduce the cluster to group the cluster which have very high relationship, which are very are related with each other. After we have that features, and also we have the training data, we can build the pure CPU model and pure GPU model. But we call it pure GPU, but actually it's considered the communication between host and device. So in that case, based on this thing, we can build up a heterogeneous prediction model based on these two pure machine learning model. This is the graph to show which combine the profiler-based model, machine learning model with the DAWL, with online scheduling, and the machine. We get the machine learning model, we get the prediction. We can inject in the step 1 and step 3 and step 4 to improve the scheduling method. So here is I briefly talk about the details about some details about the machine learning model. It's about, first we have the ML black box, and it has several very simple machine learning algorithms for linear regression, random forest, or support vector machine. And also we have we use the traditional machine learning way to get rid of overfitting for example, the cross validation and also L2 regularity. And how to evaluate the models, the machine learning algorithms, we use R2, R square. Here I show the experiment. We run our experiment in 4 type of machine. They are different in number of cores, and also they are a little bit different in the GPU. So and also then for the stencil code, we try the different matrix size, but for the sparse matrix multiplication, we use the University of Florida sparse matrix collection, and this 5 for the table 2, table 3, this 5 matrix, we use it for the testing. Here is the result. The x-axis represents the matrix size. For example, 1,000 represents 1,000 by 1,000, and the y-axis represents the speed up because based on the baseline is the CPU sequential execution time. And also they have several categories. For the GPU only, it means we only use GPU, and the Dart GPU means we run the code on the on Dart's platform and only use GPU. And also we run Dart CPU. It means we run the code on Dart's runtime with multiple CPU. And Dart stall means we use our basic methodology. First we choose hardware, and then we scheduling. Based on the model and based on the mathematical model, we choose how to allocate workload. So from here, even though and another important thing is we try to reduce the test or training time. We limited the available GPU resources to the 2 gigabytes. And then in this case, we see from even though the fourth platform, they are a little bit that the speed up are different, but the total train is very similar. It means before for the stencil code, we limited the iteration time step to 30, and when it's less than when the matrix size is less than the available GPU size, it means the GPU is much faster than the 32 core or 16 cores. So the DAO will choose the GPU and then after the matrix size was much large, so it's better to use co-running way. But even though it's co-running, but they need to synchronize with synchronization with each other, and also they need to communication with each other. So the performances were not as high. The speed up were not as high as the small matrix size. This slide shows the results. We use DAO and PDAWL at the same time. Compare these 2 methodology. Because the DAO is based on the mathematical model, but the PDAWL is based on the machine learning model. From here, we can see the PDAWL is machine learning model. We can provide a very stable estimation, and then it's a little better than the mathematical model. So here is a PDAWL run on sparse matrix SPMV. So the baseline is a single CPU execution time, and from the graph we can see the GPU may not very good for the sparse SPMV because we consider the irregular data computing. The CPU is much better than the GPU in this case, but the PDAWL can use machine learning. It can combine the after it splits the model to regular and irregular, and utilize this information. It's much better than both of the CPU and GPU. Then the conclusion is about for here we mainly focus on the PDAWL. It means we leverage the online scheduling and offline machine learning together. And also for the application, we choose two applications. There are some problems to exist. So for example, we want to add more machine learning algorithm to the black box to make our model more accurate, to increase the accuracy of our model. And also we want to try to find a way to reduce the training time. And also it's really need to add more hardware, support more hardware. Yeah, that's all. Any questions?
Thank you.
Thank you for the presentation. So if we have no questions, I think it's time for us to thank everybody.
Yeah, I have one question, very short question. If I may.
Please.
Yeah, at the beginning of the talk, I think you mentioned that at some point you can decide whether you want to execute the task or workload or whatever, either on CPU or on GPU. Did I understand it correctly?
Yes, we use the mathematical model to estimate how long you can execute on CPU and how long it can execute on GPU. We compare with each other, and then we got better.
And is it like because I know that there were some attempts, like for example from Intel, to provide these Xeon Phi architectures that were basically allowing to execute both, you know, CPU code and GPU code at the same time or something like that. Do you have some actual applications that are designed that they can be executed both on CPU and on GPU, or is it still something that is not so common?
Yeah, it's right now. I think a lot of applications can run on both on CPU and GPU. We only choose we now choose the true application. We choose the kernel, and it's not the kernel original is sequential code, and also in online they have the GPU version. They also have CPU version. We just combine them together to make the heterogeneous part.
Okay, good. If you have these applications, that's fine, because I'm not an expert in this field, so that was somehow very interesting for me. Thank you.
I have one question. If we still have time.
Sure.
Okay. I'm still. Maybe I didn't understand correctly. What is the main reason of the speed up? I mean, you saw the SPMV that is good in CPU, but the machine learning assisted model can show higher speed up. So what is the main reason?
You've muted your microphone, so maybe we can hear you.
Tongsheng, I think the question was on the reasons for the speed up. why they happen. Did I get it right?
Yes, you're right. Thank you.
I think the problem is that her mic is muted, so she needs
Oh
to.
yeah, Tongsheng, we cannot hear you. Now you unmuted.
Did you hear the last question?
Tongsheng, I think we heard you typing, I believe, or someone else typing.
Maybe we will have to read the paper.
Marcus, do you want to comment?
Yeah, I mean, I think that she has some problem with the phone. She's saying me here for the chat that she cannot hear anything, so I advise her exit and enter. So what is the question, Agumula? Please repeat it.
The question is, what is the main reason the method can achieve the speed up?
So you have a stencil code they execute in a time step. And in each time step, you can choose, for example, if a task it will execute in CPU or GPU. So maybe she joined, and you can improve the speed up if you try to schedule in a correlling way, for example, GPU and CPU. But the speed up, the correlling way, it must be synchronized. For example, if the CPU is larger than CPU, it will spend more time in the time step.
So the main reason is, the main reason is decreasing the synchronization.
Yeah, if we decrease the synchronization, we can run the application in load balancing better. Yeah.
Okay, thank you.
So for that is that we try the analytical model and we try the machine learning model like predictor, and we conclude that machine learning help to try to synchronize the load balancing. Yeah, it's
okay. Thank you.
Thank you. I think Gonzalo, he said something. Gonzalo, yeah, Rodrigo, you have a question?
Oh, that was from the previous talk. Sorry. That was my question to Dalibor that I did before.
Any final question, folks? All right then. So let's thanks everybody who participated. This was actually, to be completely honest with you guys, it worked a little better than I expected. We had all the talks.
Yeah, that's excellent. Thank you.
Thanks so much, Young-Shung, to staying so late. Very appreciated. Thank you guys all for joining all over the world. This is actually nice to, at least to me, to get some resemblance that we keep moving in despite of the pandemic. And hope to see you all in a future year when we can actually get together physically. Yeah. Although this went well, the physical event is so fun.
Yeah, I agree. Thank you all. Next year, the conference will be held in Portland, Oregon. So hopefully, if the situation will be better, we will meet there. again. Thank you.
Thank you to all of you for the meeting. See you maybe the next conference or parallel conference. Not present, yeah? Let's hope. Bye. Bye, Alfredo. See you.
Bye, folks. Good to see you all. Hey,
Okay.
Amelia.
Bye-bye, guys.
Thank you very much. Bye-bye.
Bye-bye. Thank you.